Now we'll get even more in depth about what the geometry is going to look like if we have two electron groups. Now we said that overall this is going to be a linear geometry in terms of where the electron groups are. But we're finally to the point where we realize we're going to have to make a couple of distinctions here. We're talking about the electron groups. We're not talking about atoms. So we're going to need to be able to describe where the electrons are and where the atoms are. And we need to be able to do them separately. Now here's three different example sketches of ways that we could end up with a linear geometry. And so you can see here that we could have something like sulfur double bonded to carbon, double bonded again to another sulfur. And you can see right away that, yeah, everything's got its octet rule filled. That's a fairly normal looking molecule, and it's nothing that's terribly surprising to us. So this is going to be one of our linear geometries. Now hydrogen cyanide is going to be another one of ours. We're going to have our hydrogen-carbon single bond. We're going to have a carbon-nitrogen triple bond. We have our electron pair, and if you do a quick count, you'll see that all of them are at their octet as well, and hydrogen's at its fake octet. So that's going to be a pretty stable molecule. And then we get over to this one, and you say, well, I do see that hydrogen's happy. I see that nitrogen is also happy. Sorry, I always have to say it like that because I hate acting like these things have emotions. You know, they obey the laws of physics. That's how atoms work. Okay, so it is well satisfied for its optimum geometry, aka happy. But we get to beryllium and we say, well, wait a minute. We've only got 4 electrons. This is a problem. Why isn't it at its octet? And to answer that, we should go to the periodic table for a moment. So, you can see here that we have beryllium. You can see that one of the nice things about this periodic table is that it's giving my orbital notation right over here, my box filling diagram. And you can see that I've got my 1s filled and my 2s filled, which looks a lot like the noble gas helium. And remember, we've said that that's a special moment of stability. And because of that, beryllium and boron are both allowed to kind of cheat and be electron deficient molecules. Remember, that's one of the things we talked about in the last chapter. Electron deficient molecules are allowed to have only 4 electrons involved so far, so only 2 in their outermost level. And once you end up having bonding, they're going to cap out at having 4 electrons most of the time. So you can see here that we are short electrons, but because beryllium is so satisfied having fewer electrons, that's an okay case in this case. Now all of those are going to be AX2 geometries. They're all going to be linear in terms of their shape. Because notice, when we count up the electron regions, 1 electron region, 2 electron regions. We don't care about the fact that they're double bonds. Just like we don't care about this being a triple bond, it is a single region in space. And another region, giving me a linear geometry. And same thing over here. Beryllium to hydrogen, beryllium to nitrogen. All of those will be AX2 geometries. Now, this is going to be common when we have lots of high order bonds, like you see for the hydrogen cyanide, or for the leftmost case. On the far right, with beryllium, we have the case where we have the electron deficient atoms, and those ones are also allowed to have 2 electron groups.